Hello everyone. In this video, we are going to look at how to perform the Newton-Euler formulation for robots using MATLAB Symbolic. Derivation of the equations using Newton-Euler, or the method we call forward-backward recursion, is done in one of my previous videos. If you go to my robotics playlist, you see this video. I have already talked about the derivation, right? But if you look at the example that I solved, which is for the 2DOF planar arm, you see that as we move on with more degrees of freedom, here you just only have 2 degrees of freedom, but even with 2 degrees of freedom, the expressions that we have for the reactions, the reactive forces and the torques at the joints, right? Those gets larger and larger if we want to go all parametric. Okay, so, and remember that we had to use 6 equations here. Equations 1 to 4, which we go from the base frame to the end effector, so we call it forward recursion, and these are all kinematics equations. And then equations 5 and 6, which you go back from the end effector to the base, and we call them kinetics or backward recursions. And so you need to apply 6 equations. These are all recursive equations, and 4 of them forward, 2 of them backward. And here, if you remember for this one, and you have lots of notations here, right? You have all these notations. You have R of I Ci, R of I plus 1 Ci, R of I plus 1, which are connecting the previous joint to the centroid of the current joint, the next joint to the centroid of the current link, and of course the centroid of the current link. And then you have these reactive forces and torques at the 2 ends, and everything, if you remember in these equations, is written in frame I. So the 2 governing equations here, these 2, are written in frame I instead of the base frame, so we can use a constant I matrix, a rotation matrix, rotational inertia matrix. And so our rotation equation should be on the right side expanded in 2 terms. So we had lots of these notations. Even the G, the gravity, you had to decompose it along the axis I, the frames I. We had a lot of rotation matrices, and this involves tons and tons of parameters. And the smallest mistake can easily change our equations and our total forces or total torques or anything like that. So if you want to not make any mistake, we might want to try using MATLAB Symbolic and trust the accuracy of Symbolic if we give it all the correct parameters and functions. So MATLAB Symbolic derives us these final terms here. Look, if you look here, this is the force on joint 2. This is the force right here, basically. Okay, that is F2, the total force. And it is written in terms of G2 and AC2. And G2 is this, and AC2 is that. So if you expand it, you see that is going to be quite large. And tau 2 is I2 alpha 2, which is not bad. This one is not bad. And then F2 LC2I. So you have to bring that F2, which is already big, cross-producted with LC2I, which is the distance from joint 2 to the center of member 2, right? And so tau 2 is going to be even bigger. Look at that. You see how big it is? And there is very high chance of making a small mistake. One of these positives becomes a negative or some small mistake. And now when you go back to link 1 and go for F1 and tau 1, they get even bigger and bigger. Look at that. Now F1 is what? M1AC1, R12F2, and M1G1. Okay, so first of all, there is R12, right? F2, which I just showed you. G1, which is this guy. And AC1 in this case, okay, which is this one here. So your F1, again, if you expand it, it's going to be some big term, and worse than that is tau 1. If you write the equation for tau 1, then tau 1, look at it, is going to be this, where in this huge term, this tau 2 itself is already that big of a term. Imagine, right? That whole thing is replaced just as one of the terms in tau 1. So see how big tau 1 expression is. There is no room for mistakes, so I would trust MATLAB Symbolic, and I want to show you how to use MATLAB Symbolic to implement these equations 1 to 6. So here is the code that I wrote for this problem, but I made it a little bit more general so you can basically use it for robots with other degrees of freedom or higher degree of freedom. So in this case, what I defined is t, q1, and q2 as functions of time, masses and length of members 1 and 2. I assume that the centroids are in the middle of the members. Vector omega, which is going to be a symbolic vector, and it is going to involve omega of member 1 and 2. Also omega of member 0, which is the base frame, which is all 0. The same thing for alpha. A of C's, A of E's, F's, and taus. Okay, so these are all going to be matrices, and each column of matrix corresponds to one of the joints or one of the members, basically. So here you see I create these vectors of these parameters. So I'm dealing with vectors and matrices that are all symbolic. So I put M1 and N2 into M, L1 and L2 into L, and LC1 and LC into LC. I also assume the slender bar. So here, let me add that here. Slender bar assumption for the members. The only i's they have are I about y, and z, which is ml squared over 12. And again, you see I combine these two matrices into a bigger matrix. I put them below each other and call it I. Now, one of the things when you're dealing with matrices or vectors of symbolic is this. If here I define q, okay, to be the vector of the two q's, so this is my vector of generalized coordinates, okay, you might say, what is it that you're doing here in lines 16 and 17? 16 is obvious, I'm just combining q1 and q2, right? But let me show you one problem we have in MATLAB Symbolic. So here I say sim t, q1 of t, and q2 of t, okay? Yeah? And then I say q equals q1 or q1 of t, doesn't matter, and q2, right? So I combine them into a vector. Yeah, so q here should be a vector symbolic. Now look, if I want to get my q1 back, you might say, well, just say q of 1, right? So the first element of q should be what? Should be q1 of t, right? Look here. Did you see what happened? This q actually is not considered a vector here. It is treated like, look at the dimension of it. It's a 1 by 1 sim, not 1 by 2 or 2 by 1. You see? So if I say q of 1 or if I say q of 2, it doesn't matter. It gives me both of them. So I cannot later access these individual elements and take derivatives of them to get q dot and q double dot. Okay, yeah, you see that? So what am I doing here? Look, if I just run this portion, and n here, by the way, is the total degree of freedom that you have. Here, what I did is I combined q1 and q2 into something called q vector, right? And this q vector, if you call it, it's the same as the previous q. And now this q vector, again, if I say 1, look, it gives me both of them. Now, if I want to access the individual ones, this is the trick that you have to use. You say q equals q vector of t, so you assign this q vec with t. Remember, this t is very important. You say q vector of t is, you assign it to another variable q. Look what happens here. So you assign q to another q vector with t to another q, Now look, Q of 1, Q of 2. Do you see that? If I go back here and show you, look, my cubic is 1 by 1 sim font, but my Q is what? 2 by 1 sim. So this is a trick that you have to use if you want to convert it into what? Convert it into a 2 by 1. So here, let me add an explanation for you that cubic is 1 by 1 sim, but Q is 2 by 1 sim, which can be used later. So I can access elements of it, I can take differential or derivatives of it, and so on. Similar thing is done here on the DH table. So here I'm putting the DH table for this robot and perform forward kinematics on it. You might say, why do you need forward kinematics? Because if you look at these equations, one of the things I have and I need is r of I minus 1 in I, or the transpose of that. So I need these relative r's, and I need absolute r's, r of I in 0 or 0 in r. And these r's, these relative r's, if you remember, these are what? These are those A matrices that we have in DH, correct? A's. Now, of course, this is AI inverse because R of I in I minus 1 is AI. So this is like that. And not all of it. Remember, this A is a 4 by 4. So what I need is only the 3 by 3 minor of it. So here I have to say this is the 1 by 3. This is the 1 to 3, sorry, and 1 to 3, and then of course transpose. And similarly, this guy, if it was I to 0, it was now those T matrices that I have, Ti, again 1 to 3 and 1 to 3, right? And again transpose. So I need the A's and I need the T's in DH. And if you don't know what I'm talking about, all you need is to go back to my playlist robotics and look for what? Look for the videos I have on forward kinematics using DH method. So if you go down up the list, you should be able to what? Find the here in these two. Forward kinematics using DH convention. In these two, I explained the A matrices and the T matrices, okay? So you can look at them. So you see, I need those, and another place I need them are the Z's. The Z's are the third column of these R's. Okay, so this one is what? This is the third column of this R, or you can say this is the Ti, but what? Since this is I minus 1, so you should go to I minus 1, right? And then you need to go what? The third column. So you go rows 1 to 3, but column 3. Okay, so you see, I need to perform forward kinematics so I can calculate my omegas, alphas, and once you have omegas and alphas, from there you can calculate the A's of the centroids and A's of the right ends or the endpoints of the members. So here I have my DH table. Now again, because this Q1 and Q2 are functions of time, although L1 and L2 are constant symbolics, this DH table, okay, becomes 1 by 1 sim. Look here, when I run this, you see, this is my DH table where this is the theta, this is the D, this is the A, and this is the alpha for each frame, between each frame and the next one. And again, if you look at DH table, you see it's 1 by 1 sim. So if I want to access this element, I cannot say, hey, give me DH underscore table element what? Row 1 and column 2. If I do that, it gives me an error. And say, hey, what are you talking about? This is a 1 by 1. I don't have element 1, 2. So again, I use the same trick that I used above. So here, let me add that dh underscore table is 1 by 1 sim. But if I come here and say that whole dh table of t, assign it to this new variable dh, now dh is what? Is a basically 2 by 4 sim. Okay, look here, if I assign this to dh, right, and now look at dh, look, 2 by 4. So now the thing I couldn't do with dh table, I can do with dh. Look here. Or if I say 1 and 3, it should give me L1. Okay, so when I get those A matrices based on the DH formula, I need to access the elements of it. I need to access cosine. This is cosine of theta here. This element here is the theta, right? This is theta. This is alpha here. And so this one here is the A, and this one here is the D. Okay, so I need to access them row by row. So what did I do here? I go from I1 to N and I calculate all of the A's. And I'm not giving them different names, so I'm not going to call them A1, A2, A3. I'm going to get all A1, A2, A3, but I'm going to put them in the third dimension of matrix A. So matrix A is like what? Matrix A is like A1, semicolon, A2, and going down if you have more degrees of freedom. So the top portion of it is A1, the first dimension of it. And the second dimension of it is A2, or let me, actually that's not right, this is right. The first dimension of it is A1, and the second page of it, of the third dimension, is A2, something like this. Okay, this is how I store it. Now, I need to get the T matrices. Remember, T1 is A1, T2 is A1 times A2, T3, and so on. And T2, I can write it as A1 times A2, but A1 is T1, so I can write it as T1, A2. So here, look, I'm calculating my T's using a for loop. And you might say, why do you bother? It's just 2 of them here. Just write it. Yes, but here I'm doing it for the case that n is bigger than 2. If you have 3 or 4 or more degrees of freedom, then you don't need to type all of these formulas one by one, or this one here. This automatically will fill all of the A's for you. This will automatically fill all the T's for you. And the Z's. Look, I get the Z's as well here. Okay, so all of the things I need for my later forward recursion, I'm calculating them all in for loops. So if later I come and change this n to 4 or 5, and I expand this DH table, it can easily accommodate for me. So I'm writing it general case for you. Okay, yeah? And now, again, you see these different dimensions of T are safe for T1, T2, and so on. So again, I have something very similar to the top portion here, that T, first page of the third dimension is T1, and the second page of the third dimension is T2. Also, I use the fact that Z0, Z of the base frame, is 0, 0, 1. Okay, and I fill the rest of the Z's. Now, we need to do what? We need to define the rest of the thing. So here, look, I say get the derivative of Q number 1, which is Q1 of T, with respect to T, get derivative of Q2 of T with respect to T, and call them Q1 dot and Q2 dot. And then what? Go ahead and store them here into this vector Q dot vector. And again, this Q dot vector is what here? The way we did it, this Q dot vector is a 1 by 1 sim. But by doing the trick, now Q dot is going to be what? Is going to be a 2 by 1 sim. And if you don't like to create these extra variables Q dots that you never use anywhere else, you can get rid of these lines 44 and 45, and you can directly bring this guy right here and bring this guy what? right there, like that, and get rid of these two. Okay, so we can do it this way. Similarly, the second derivatives for Q1 and Q2, which we call Q1 dd dot or double dot, correct? And Q2 dd dot, we can assign them as the two elements or entries of vector Q dot. And then what? Since this guy is a 1-by-1 sim, I'm going to assign it to the new variable qdd dot, which is now a 2-by-1 sim. Okay, then R here is the huge matrix that involves all of the R's that I need. If you remember, I need two types of R's. One is the relative R between two consecutive frames. The other one is the absolute R that I need for each frame, okay, with respect to the base. So the way I store them here is I go to the ith row, or ith, it's not really row, I would say, if you call it a block matrix, ith row of the block matrix is in the ith row, or 3 times I rows. First, I store I of I minus 1, which is basically I with respect to I minus 1, the transpose of this. And the next one I store is what? R of I with respect to 0, which is again what? The transpose of this one. So these transposes that I need, I store them in what? In the left side and the right side of this matrix. And if you see, I'm doing it for I1 to n. In other words, the structure of the R is what here? So R is going to be like this. First goes R of, basically, since I is 1, right? So we go R of 1 with respect to 0, and then again R of 1 with respect to 0. In this case, the relative and the absolute are the same. I put them next to each other, and then I go to the bottom section, and now I do R of 2 with respect to 1, and then R of 2 with respect to 0. So I store them like this, a block matrix R, so I can access them later. Okay, and is that it? No, I need another another 2 R's. What are those 2 R's? That is for the end effector frame. So here, basically, I have 2 with respect to 1 and so on, but I also need something for end effector. Okay, because if you look here into my backward recursions, I also need to have F3, which is the forces applied to the end effector, and tau 3, which are torques that are applied to the end effector. Okay, and in this case, they are what? They are 0, or we can assume they are 0, or we can what? We can assume they are not 0. Okay, here I just go with assuming that the robot is just doing its motion without any external interference. So we assume these two are 0, but if you want, you can change them. And if that's the case, then I need to write an equation between 3 and 2. So if you look here, let's see. You see here, I have 3 and 2, F3, F2. So if I go and look at this equation number 6, what do I need? If this Fi plus 1 is 3, and I is 2, then this rotation matrix will be rotation of 3 with respect to 2. So I also need rotation of 3 with respect to 2 as well. Okay, what is rotation of 3 with respect to 2? In this case, if I attach a frame to the end effector, since end effector is rigidly attached to member 1 here, then the frame 3 is going to be just like frame 2, the same frame. Okay, so this is going to be your y3 and this is going to be your x3. Okay, so R of basically 3 with respect to 2 is going to be the identity matrix. And if I need R of 3 with respect to 0, I don't really need it, but if I do, that's the same as R of 2 with respect to 0. Why do I need it? Because of the format that I'm storing that big matrix R, I also need to have these two right next to each other. So here, look, I say the left side, which is R of, here, this guy is R of 3 with respect to 2, that is identity matrix, and here R of 3 with respect to 0 is what? Is the same as R of 2 with respect to 0. Okay? Yeah? And so I need to bring these guys as well. And here say R of 3 underscore 2 and R of 3 underscore 0. So now this R is going to be that huge matrix, which is basically it has 9 rows and 6 columns. Okay, is a 9 by 6 sim. So now that I have all the entries that I needed for my forward and backward recursion, let's go and apply the equations. So here I start my W as a bunch of zeros, the same with alpha, A, and C. So these are just initialization. And then I say omega of 1 equals 0. So here omega is the same as W. And remember that the base frame does not have any angular velocity or any angular acceleration, and it does not have any centroid or endpoint that moves. So that is basically this part of my text here, that I say we start from the base frame since it has no motion and move on to what? Move on to the frames afterwards. So here, these are what? Base frame is stationary. And these are what? These are just initializations. Okay, and the structure of this W is what? If you look at it, it's zeros of n plus 1 and 3. So n is 2, so it's going to be 3 by 3. And what you will put in it is W0 and then W1 and W2, or omega 1, omega 2, and omega 0. Okay, they go and will be stored in the columns of what? In the columns of this omega. And same thing goes for what? Same thing goes for alpha, and same thing goes for AC and AE. There we go. So I added all the comments for you so you can easily read it. Now, here are those equations. So this is the update equation for W. You see, omega I equals transpose of the R times Wi minus 1. What is that? Let's go and look. That is this equation number 1. As I said, if you look at equation number 1, you see omega I is this R matrix times omega I minus 1. This R, if you remember, we stored the transpose of it. We stored I to I minus 1, not I minus 1 to I. So we need, whatever we stored, we need to transpose it, multiply it by this. This also, we stored the transpose of it. And these Z's we found earlier, and Q dot is simply what? Q dot of I minus 1. This is the element in that vector Q dot. Okay, so if you look here, you see here is these two transposes are used, so we get those matrices that we want. This is the Z, and this is the element of what? Q dot. So I can say this guy here is what? This is equation number 1, right? Similarly, I have what? Equation number 2. And then we go down to equations 3 and 4, where you see this omega dot is the same as alpha that we have. And again, we have these R matrices. We have RICI in it and RII plus 1. We need these two vectors. And based on the definition that we have, RICI, as you can see, it is along what? It is along the axis that it has. So for instance, here, the R that connects this E to that C, or that I to that C, it is along this X, the own X, like if it's member 1, it's along X1, and the distance of it is LC1, you can see it here. And then R of I to I plus 1, which is 1 to 2, is the same direction I, but it's the total distance L1. Okay, so I'm using these guys, these 4 here, and I wrote the formulas for them, these guys here, right? You can see them there. So here, this is your equation 3. And finally, what we have, equation number 4. The only difference, as I said, is replacing basically LC1 with L1 and LC2 with L2. And that is already taken care of here. Okay, so these are equations 1, 2, 3, and 4. And once it's done, you see it goes from 2 to n plus 1. Why 2 to n plus 1? Because for 1, that is going to give us omega 0, alpha 0, AC 0, and AE 0, which they're already taken care of. So I just need frame 2 and frame, or I of 2 and I of 3, which are going to give us omega 1 and omega 2, alpha 1, alpha 2, all the way. So here I'm going to show you the results, and then I go for backward recursion. What I do is first I set the end effector force and end effector torque to 0, but before that I do initialization, right? And you see here, again, I set the end effector force and torque to 0. If your application has a force or torque on the end effector from environment, you should change them here. The G vector that we have in the code here, it's really a matrix, not vector. And you see it's sims of 0, 3, and n. So in this case, it's going to be 3 by 2. So the structure of this GVec is what? It is G1, and then what? Right next to it is G2. And G1 and G2 are the projections of the gravity onto frames 1 and 2. So this one here, and basically this one. Okay? So you see I started them at 0, but then as we go through the backward recursion, I keep filling them. I basically bring the absolute R here, transpose it, and since this G of 0, negative G and 0 is in frame 0, I bring R of I in 0, and then transpose it, so it's going to be 0 in I, and then R of 0 in I times that is going to take that G, which was in frame 0, right? So this is going to be R of basically 0 in I times G that is in frame 0. Okay, and that is going to give us what? G in frame I. And that is what I use here. Then I go to my F equation. So this is going to be equation 5. And finally the tau, which is the largest equation, even in MATLAB, that is equation 6. If you look at them, if we go up here, look at equation 5, what we need for it is that rotation relative matrix. We need those G's, we need the AC's that we found in equation 3, and we need the F afterward that. So here I need to go backwards. So if you look at my for loop, you see it is going from n to 1 with increment of -1. So this is backward recursion. And this is exactly what you see over here. The next f, this is that r, this is the g vector, this is the ac that I calculated here. And the torque is very similar. We have the rotation matrix relative, RICI, which we had earlier, F, tau next one, the R, and the I's were stored in the big matrix I, the alphas, the omegas, these are all already calculated. The only vector here we have extra is r of I plus 1 to see, so it's coming back, it's this vector, from the end of the member back to the centroid. And clearly, if you look in this case, it is what? It's in the I direction with the negative sign with magnitude of L1 minus LC1 and L2 minus LC2. So we are going to implement these two into our equation, and you can see that right here. Okay, so now equations 5 and 6 are applied, and then I can see the g vector if I want. I can see f and I can see tau. Okay, so here by running these two sections I can get everything symbolic. So let's go ahead and run it. Here is this part, then we run this part, then we run this part, then we go to forward recursion. And if I show you the result of forward recursion, look, everything does make sense. The first column is omega frame 0, all zeros. The next one is omega frame 1, which is just q1 dot. The next one is omega frame 2, which is q1 dot plus q2 dot. Similarly for alphas, I have q1 double dot, and here I have q1 double dot plus q2 double dot. And then I have a of c, here the first column is a of frame 0, which is 0. Then I have, look here, negative L1 Q1 dot squared over 2 and L1 Q1 double dot over 2, which are exactly these equations. If you look at them for AC1, look, that's exactly this. If you replace LC1 equal to L1 over 2, that's exactly this one. And then you can get A of E1 as well here, which I have it. If you look, that's the same thing, except it's L1, not L1 over 2. And then this one here is basically, if you read it, you clearly see that this is what, this is the A of C2. Let's just look at one component of it here. So it's negative L2 over 2 times what? This is basically Q1 dot plus Q2 dot squared. So negative L2 over 2 Q1 dot plus Q2 dot squared, and if you look at that, that is exactly this guy here. One of your terms is negative L1 Q1 dot squared cosine Q2, right? And again, if we go back, you should be able to see that. Negative L1, you see Q1 dot squared cosine Q2, and this one is what? L1 Q1 double dot sine Q2, and that is this guy here. You see, so I can get each and every one of them without any mistake. And these are all ACs and AEs, different columns. Then I go and do my backward recursion, and that is going to give me all the F's and the taus. Here we go. These are the G vectors. Clearly, you can see that, right? This is G1, the first column, and this is G2 that I had in my notes. Look at them here. That is G1. This is G2. And then the F's and the taus, right? Those big terms that we have for F2 and tau2, look, all of them are here. So here we go. Again, here, the first column, this is going to be large. The first column is F1, and the second column is F2. Right? And then tau 1 and tau 2. And look how big tau 1 is. Look at tau 1 and tau 2. You see how big it is? And this last column is, of course, tau 3 and F3, which should be 0 and all zeros, as you can expect. Right? Look. And if you want them, you might say, can I have like F1? What is F1? Well, F1 is the first column of F. So if you say F of all rows in column 1, Look, here we go. So this is what? This is your F1. Yeah, that's what it is. And you can write it in a Peretti way, right? You can use the Peretti command, you can use simplify, you can do whatever you want. And once you plug in numbers for M, G, L, and so on, then it becomes just a bunch of numbers. And I'll show you how to do that in the next part of this video. But you see here, I can get all of them. So now that everything is calculated perfectly symbolic, I want to show you how to do some numeric using all these correct symbolic equations. So here, we want to do inverse dynamics numerical, which basically means what? We know the Q's, Q dots, and Q double dots. We want to find the F's and the taus. Okay? We want to find the reactions or the required torques. So here I pick two time functions for Q1 and Q2. This comes from your task. So this is basically your path planning that gives you some functions for Q1 and Q2, right? So I can say they come from what? Path planning. So let's say these are my functions. One is 0.5 t squared, the other one is 0.8 t squared, or I can even make it t cubed if you like. And now what? Here I pick some numbers for M1, M2, L1, L2, and G. Of course, G you cannot just pick. And then, before I pass in the time, I use the subs command to what? To carry all the derivatives for me. Because right now, the F's and the taus are all written in terms of what? In terms of all these diffs. When I use the subs command, it plugs in that quadratic or cubic function for Q1 and Q2, carries all the derivatives, and give us simplified version of what? All of those 6 parameters. W, alpha, or omega, alpha, AC, AA, and F and tau. So look here. I run this portion for you only so you can see. Look. Look now, you got much better results. So look here. You see? This is Q1 dot, this is what? Q2 dot, right? Or Q1 dot plus Q2 dot actually. This is Q1 double dot, this is Q1 double dot plus Q2 double dot. And now if you look at your AC or AE, they are much smaller because all the derivatives are calculated. Still, you have some big fractions, but if you use the VPA command, if you want, you can get rid of these and replace them with decimals. So now they are not going to be as long as last time. They are going to be much better than last time. And now what do? Now I start plugging time values here. So I go from time of 0 to time of final, which in this case 4 seconds. You can change it with some increment of 0.2 seconds. And then I get a number for t. Then what? Then I store that in a vector t numerical. And then what? I convert this simplified W or alpha or A or F or so. I first convert them to decimals. How do I do that? I use the command eval first. Eval will evaluate all of those time functions because now if you look at them, they're only time functions. They're all only pure time functions. So as long as I plug in t, I should get numbers. But since those numbers will be big fractions, not decimals, I use VPA and then as many decimal places as I want to convert them into decimals. Then, although they are still decimals, I cannot really get the norm of them. And you might say, why do you need norm? Because I want to see the magnitudes here, specifically for F and tau, right? I want to see the magnitudes of the forces and the torques, but here I can also get the magnitude of omega, alpha, AC, and AE. And remember, the structure of them are matrices, right? The structure of them are what? Clearly matrices here, like here or like there. So what I need to go to each column of that and take the norm, okay? And in order to do that, there is this new command that you can use called vecnorm. Because if you give a matrix to the norm command, it gives you a single number for the entire matrix. But if you want to get norms of columns of a matrix, you use the command vecnorm. So it gives you norms of columns and it returns a vector instead of a vector of norms. But this command only works on double variables. This VPA still is not a double, it's kind of a symbolic again. So I use a double first so I can apply the vecnorm. You see how many functions I need to use to get those? Then I increment my time index, and now I go and plot all of these for you. Okay, yeah. One last function I wanted to mention for you is here in the figure 1, I have 4 subplots, and I want to use one title for entire figure, not per subplot. So I want to add one title which shows my functions here. I want to use one, and if you want to use one title for the entire subplots, instead of using command title, you have to use SG title. So this will create one title for the entire for the entire plot for you. So let's go ahead and run the final code, and you can see the numerical results here. There we go. So these are what? These are the plots of F1 and F2, the forces on pin 1 and pin 2 for 4 seconds in Newton. And these are the torques that you need at joint 1 and 2 for, again, 4 seconds for torque 1 and torque 2. Clearly, you see torque 1 is much more because it carries a lot more load on it. And then you, of course, have what? The magnitudes of omegas, alphas, ACs, and AEs, okay? And these are those things here. Now you might say, are AC for 1 and AE for 1 are 0? No. That's because here t cubed grows much faster than t squared, so one is much bigger than the other one. Okay, if you made both of them square, like last time I did, then it should not be what? That huge of a difference. So if I can go back here and just make it t squared, it should not be basically such a huge difference. Here we go. Okay, so this is F and tau plot for both of them quadratic, and these are AACs and AAs and how they change versus time. And the torques will tell you what is the max torque that you need on joint 1 and joint 2, so they can tell you basically what kind of motors to pick. And F1 and F2 will give you what? Will give you the forces on the pins, so based on that you can design the pins. Okay, you need to know what kind of material, what cross section you need for the pins, and you need to do fatigue design to design a proper pin, and I have a video for that one as well, right? Just the last reminder that if you go and look at one of my latest videos is the one that is a pin design. Let's see here, fatigue for a pin design, okay, and you can see it here. Okay, so hopefully this video was useful to you, and I explained line by line of the code, so when I give you a download link and you use it and play with it, you know exactly what you should be doing. Thank you so much for your attention. I'll see you in the next video.